G'day fam, welcome to another video. This one is on the topic of conservation of energy. So energy is conserved when transferred from one object to another in an isolated system. In stage 1 physics, the expectation is that you'll be able to solve problems using conservation of energy and that you'll be able to describe and explain the energy losses that occur in systems involving energy transfer. So the law of conservation of energy states that energy may be transformed, but it is never created or destroyed. And as we've touched on in our previous videos, we know that work is done to gain kinetic energy. So work is equal to the change in energy or the change in kinetic energy. So for example, if we are pushing a stationary object, we are doing work on that object and transferring kinetic energy to that object. Similarly, if we're stopping a moving object, just say we've got the same object moving with velocity v in this direction, then if we're stopping it, we're reducing its kinetic energy, half mv squared, all the way to 0. So that change in kinetic energy to bring whatever kinetic energy it had to 0 is equivalent to the work that we're doing on that object. So in the situation of a falling object, we might have to describe what's happening at each point or at points along the fall. So if we start at the top, the kinetic energy is 0. So we're talking right at the stop before it drops. The kinetic energy will be 0 because the velocity is 0. The potential energy will be equal to the ball's mass times by gravity times by whatever height, h, it's at. Halfway or thereabouts, the total energy will be equal to the kinetic energy plus the potential energy. So because its height will have reduced at halfway, it will have lost some of its potential energy or gravitational potential energy, but because the object or the ball is moving, so it's got velocity, it will have gained kinetic energy. And we know from falling objects that the acceleration is constant, but the velocity increases as the ball or any object drops. So its kinetic energy will be increasing whilst its potential energy decreases. At the bottom, so at the instant just before it hits the ground and stops, the kinetic energy will be equal to half mv squared, so whatever velocity it has squared, times by the mass times by half. However, its potential energy will now be 0 because the height will be 0 meters above the surface. So potential energy is transformed into kinetic energy. So the change in kinetic energy is equal to the negative change in potential energy. Another way of writing this is kinetic energy minus the kinetic energy to start with is equal to the negative potential energy minus the potential energy to start with. If we expand our brackets, this will become a negative EP plus EP or electric potential energy to start with. And then if we rearrange, we'll get EK plus EP equals EK to start with plus EP to start with. And that is indicating that mechanical energy, so the sum of potential energy and kinetic energy. That's confirming or highlighting that this energy is conserved. So whatever energy a system has before is the same as the energy that the system has after. So now for an example, we've got a 78 kilo skier at 1400 metres above sea level, and they accelerate from rest to 1300 metres above sea level. What is their final velocity? So we know that the kinetic energy plus the potential energy to start with is going to be equal to the kinetic energy and plus the potential energy to finish with. So this will be half mv squared plus mgh1, and that's equal to half mv squared of the second kinetic energy plus mgh2, so the second height. We know that the velocity to begin with is 0 because they start from rest. Therefore, this here will be 0 because this initial velocity is going to be 0. So that means that we're left with mg height 1 is equal to half mv squared, and that's the second velocity, plus mg height 2. We can simplify this so we can get rid of all of the m's, because if we divide both sides of this equation by m, all the m's are going to cancel out. Then we're left with gh1 is equal to half v squared 2 plus gh2. This can then be rearranged to half v2 squared is equal to gh1 minus gh2, and this can be further simplified to v squared equals 2g h1 h2, and then finally v squared equals the square root of 2g h1 h2. If we sub in all of our values, we'll get v2 is equal to 2 by 9.8, and then height 1, which was 1400, minus height 2, which was 1300 metres above sea level, and then pop all of that into your calculator. You'll end up with 44 metres per second, and that is the final velocity of the skier, or the velocity when they're at 1300 metres above sea level. And lastly for this video, wasted energy. So energy transformation is rarely 100% efficient. There is a quantity that is wasted as a non-useful form. Often this is wasted as heat energy. A cause of this waste is friction. So because of friction, energy is wasted overcoming friction. So therefore the total energy that you're putting into something isn't the same as the total useful output energy. So wasted energy is equal to the total input energy minus the useful output energy. So whatever the difference is between those two will be your wasted energy. And energy efficiency is the ratio of useful output energy to the total input energy. This can be found in a number of ways. You can use the useful output energy and then divide that by total input energy and then multiply by 100 to get your percentage. Because energy or change in energy is equal to work, you can also use useful work done divided by total work done and then times that by 100 to get your efficiency. You can also use output power divided by input power times by 100, and we'll touch on power in the next video. So as an example, we've got a car engine, and the car engine transforms 50 kilojoules of energy from fuel into 10 kilojoules of kinetic energy, so 10 kilojoules of energy for movement or motion. And we have to work out what is the energy efficiency percentage. So we know that percentage efficiency is equal to useful output, sorry about the writing here, energy, that curly E is, I'm going to use it to represent energy, and then that's divided by total input energy, and then times that by 100. So subbing in our values, we've got 10 kilojoules of useful output energy, but we're putting in 50 kilojoules of input energy. So 10 over 50 times that by 100, that'll be equal to 20%. So our energy efficiency percentage is 20%.